Another thing that we discussed was the built-in optimizations. As we mentioned earlier, these optimizations made this study possible because we were able to do the large field maps that we showed that allowed us to show beamforming in action. We ran some simulations and recorded them on a high-end desktop workstation, and we recorded the runtimes that we got in our simulations and compared them to what we would have gotten if we had taken our baseline simulation and had to run it 128 times, once for each transmitting antenna element. So before any optimizations, a single antenna at the transmitting base station and a single antenna at the device takes about 53 seconds to simulate all of the routes and points in our scene. When we applied the acceleration that we talked about called APG acceleration, this dropped to about 35 seconds. And when we then simulated our MIMO antenna with 128 elements, again to the route and the 16 devices in the scene, the total runtime was about 76 seconds for our MIMO simulation. If, on the other hand, we had simulated each individual antenna one at a time, the total runtime would have been about 113 minutes. So this was about 89 times faster. We also simulated a field map in the background with about 66,000 points. This field map was used to display the beams. It was not part of the calculations of SINR or received power, but it was used to display our beams on the map across the scene so that we could see what they looked like. So with these 66,000 points, our initial simulation took a little over 3 hours to complete. When we applied the APG acceleration, it completed in about 3 minutes. And when we then expanded from a single transmitting antenna to 128 antennas, it ran at about 37 minutes. And again, if we had taken our original 3-hour simulation and ran them one at a time, it would have run for about 16 days to complete. So we see a speed up here of about 600 times. This kind of speed up is important not just because it reduces the runtime, but because it allows an analyst to run several different conditions, change something, look at a case, run simulations again. So the speed up in runtime when we're talking about massive MIMO arrays is extremely important. So in conclusion, we've presented a new and efficient method for predicting detailed channel characteristics for massive MIMO using our new wireless InSite MIMO capability. We simulated massive MIMO in a small cell, and we generated channel matrices from our simulations. We then used post-processing analysis to compute maximum ratio transmission and zero forcing beamforming, and we showed results from our calculations of power, interference, and SINR. In this particular case, zero forcing was much superior when there was good channel state information, but when we introduced pilot contamination, it had a severe effect on that performance. This study has demonstrated the MIMO capability, and it provides some insight not only into what MIMO beams look like in a complex urban setting with a lot of multipath, but it also shows the kinds of things that you can look at when you have a good MIMO simulation capability to help you assess beamforming solutions.